So agentic workflows are RAG, except with a cycle with a loop where an agent can not only retrieve the information, but also identify and self-evaluate and identify is this information that I'm retrieving, is it correct? And then it goes through an entire loop and process cycle that it does to get the correct answer to the user query. Transformers, we know from attentionals, all you need are the crux behind most modern LLMs. We have tokenizations. Typically, we use subword tokenization just because using at a word level or even character level is going to cause vocab issues. And we all want to contain the root of certain words. So play versus playing. We want to make sure that we capture the semantic meaning by capturing the root word. So that is why subword tokenization is used, positional encoding. We want to encapsulate the meaning of the positions themselves, so the order of the words matter. So we add that to the embedding that we have. Attention is where we look at all the other tokens in the sentence or in the sequence, and we see how much attention or focus should I put on each of these other tokens. We have a transformer block consists of the attention, which looks at how much weight or focus should I give to all the other tokens, and then per token reasoning is developed through the feed-forward neural net, and this is composed of doing the expansion phase and then the compression phase. Expansion phase tries to identify the hidden features or the latent features, compression to a larger space, and then compression reverts to the original dimension space that we have. Transformer blocks attention F and N, and we can have multiple transformer blocks. Each one learns a nuanced relationship, a deeper relationship semantically with the sequence of words. And we have Laura, which is all about how can we train more effectively. Fine tuning as we take a pre-train RNN or pre-train LLM, and then we tune it on and train it on uh our data sets. And typically full fine tuning is expensive. We don't want to do that. We want to freeze the weight matrices and only update the what we call the AB matrices. And the strength of that update is referred to as the rank coefficient. QKV vectors. Q is this is what this is what am I looking for? Key is this is what I offer. V is the value that this vector offers if it were to be selected. The dot product of QKT represents the similarity across different tokens. A high similarity means that this token should pay more attention to this token. Low similarity means that they are dissimilar and they should not pay close attention to them. And then after we do our dot products with Q and KT, we do the normalization softmax to get to a distribution of all the tokens that it should pay attention to. So 50% may be on token A, 25 on token B, 25 on token C if there's three tokens. And then it does the weighted average of weights these by the value vectors to get for every single token, this is the weight. And then we weight those by the value vectors to get our new embedding that we add to the original embedding. So we're not replacing any information. We are simply adding this to the original embedding. Same thing with positional encoding. We add it to the original embedding so we preserve the information. Kafka, we know, is like a conveyor belt. You can publish topics to it. You can publish to a certain topic, and then you can subscribe to a certain topic. Producers, publishers send data into Kafka. Consumers are the ones that are collecting data from each of those topics. Partitions, each topic split into partitions. We have worker nodes at each partition. Offsets referring to how far have I actually read. So if you were to do reading from a certain an analogy is a conveyor belt. You want to see, okay, how far have I actually read? And so then in the next time, you can pick up where you left off exactly. Consumer groups, durability. So Kafka persists on disk. It's not just in memory. So how this works is, let's say you want to publish some data to a Kafka topic. So then you would send that to a Kafka topic, which is partitioned. Consumer groups may then collect the data from that Kafka topic It's distributed, so it runs across many servers, fault tolerant, throughput. The conveyor belt system. So the producers are like workers placing boxes. Each box is like a message or event, and they don't care about who picks it later. Their job is to only place them on the conveyor belt, only place the messages or the data on the conveyor belt, which are the topics. So one belt may be orders, clicks, payments, and within those belts, you can have many parallel belts. So you have under the orders topic, you can have many parallel belts, and what this allows you to do is the workers standing by the belts can pick up the boxes, and the different teams can have their own workers. So you don't need everyone to be at belt one, right? You can have some workers at belt one, belt two, belt three, and they can pick up the data that they need from those respective topics. Airflow is orchestration tool, coordinates tasks, SQL queries, Python scripts, orchestrates and manages the execution of these DAGs and tasks and dependencies. So we have operator, scheduler, executor actually runs the task, metadata stores the task status, logs, execution history. We also have ETL pipelines, inner working, stateless execution. So yeah, every task is independent. There's no shared memory. Parallelism, so independent tasks can run in parallel. Few other topics. So now we have CPU, GPU, and TPU. CPU is like the general brain system. It's best for sequential tasks. Few powerful cores. So it's like a skill general GM handling many tasks one after another. So it is sequential GPUs, parallelization, huge team of workers, all doing the same task, painting thousands of pixels simultaneously. So GPU does best at parallelization, and then TPU, tensor processing unit, it's specialized for one specific task and very extremely energy efficient. So CPU general purpose logic flexible, sequential, not parallel. GPU is parallel, and then TPU is specific accelerator, specialized RNN. RNN one layer is not a one recurrent neuron. We just have we have an RNN, we have a recurrent cell, and that entire cell consists of hidden states and output states. Hidden state is updated with the previous hidden state along with the current input state. Multiple layers, stacked RNNs, step-by-step flow of order of the entire cycle. So we have forget gate as what you want to remove from memory. This is LSTM, and LSTM solves the problem of trying to LSTM captures long-term range dependencies. So it not only focuses on the immediate surroundings, RNNs, you forget what was even in the beginning of a sentence, but LSTM allows you to capture long range dependings through these gate systems. Forget gate decides what to remove from memory, input gate, what new information to store output, what part of the memory to output. So the memory is updated through the cell state. Cell state contains the long-term memory. Hidden state is what gets ultimately gets filtered from the cell state. So cell state forgets some memory, adds some new memory, and then hidden state is the filter version of that cell state. Forget input output gate, LSTM3 gates. Transformer, as we talked about, QKV vectors, compute attention scores are the dot product of QKT, normalized through softmax, weighted sum of values, or the attention or right from the attention weights. Repeat for each of the tokens. So the dimensionality of this is number of tokens by the dimension of the embeddings, and this represents the context of the vector, the meaning of each of the tokens. Then this gets updated as you pass this along through each of the transformer layers. Residual connection means that we don't throw away the original input, we add it to the original embedding. We add the positional encoding to the original embedding. We also add the new contextualized representation to the original embedding. So the original is not lost. Layer normalization, so we make sure that the training is stable. So this is typically just standard norm. we add residual again. So what this is, right, is we do our attention layer, then we add it, then we do layer norm, then we do MLP feed forward neural net, then we add residual again, then we do transformer layer. That's the entire transformer layer, and then you can have multiple of these transformer layers. So you add residual after the feed forward neural net. Right, so each token is processed independently. So this isn't the entire expansion compression piece. Expansion, you try to identify the hidden latent features, and then you then compress it back into the original dimension space, and then add residual again, and then you do this n number of times to n, referring to the number of transformers that you have. Encoder is each token can attend to all of the tokens. So it's bidirectional context. Decoder is each token can only attend to past tokens. So this is similar to only predicting next token generation, and that's what LLMs are. There are merely next token generation sequences. Decoder masks self-attention, cross-attention, so only sees past tokens. Bag of words. What does bag of words do? Bag of words is continuous bag. It's a neural net. It's a neural net, and it doesn't consider the order of the words, which is why it's considered a bag of words. There's no intrinsic order to them. And what do they do? From the surrounding words, we try to find what the target word would be. So it is almost like fill in the blank using neural net, skip gram opposite from a target word, predict surrounding words. And that is word to vec. And that's how embeddings are learned, right? Embeddings are learned. Positional encodings, we know the formulas for those. Residual connection, full transformer layer, what changes between blocks. So block one, grammar relationships, then we improve phrasing. So as you add more blocks, you get more nuanced connections between an understanding of the relationships between the tokens. We not only have a single attention head, we have multiple attention heads. It's the same three learned matrices, QKB learned matrices, but we split them, and they do their processing respectively on each of the attention head, and then we aggregate them all together. So they're not learning, each attention head is not learning the separate matrices, so the matrices are QKB the same per transformer layer. Right? We break each of the QKB into H smaller chunks, split into H heads. So they see a smaller subspace and learns a different relationship. Linear projection split into heads. Each head does attention independently, then we concatenate and then project. And then again, transformer layer, feed forward neural net is again, transformer layer is feed forward neural net, which comes after the attention phase. And you can have a single attention head, you can have multiple attention heads. And then you do residual connection, add it back to the original embedding. So nothing is lost. You do layer normalization. You layer norms, F and N expansion, nonlinearity, compression. And the reason why you do the expansion compression is to capture the hidden per token reasoning, not just cross token, not just identifying which words I want to pay attention to, but after I've done that, is thinking with the token itself. Like what does the token represent? Excluding what other words imply about what that token represents. And then here is how we actually get. So temperature is a way to control the randomness of the next token generation. So after we compute the attention scores, right, the way we can apply a temperature is we divide by T. So it's the softmax of QKT, and then we divide by a temperature T. We also normalize by root dk, and we divide by a temperature. And low temperature means that the differences become bigger, model becomes more confident, so it picks the top option more often. So it's very deterministic. High temperature makes the distribution more stable, so you have some more randomness and unpredictability when it does the next sequence predictions. And how does it generate the logits, right? How does it generate the logits, right? It has now vector embeddings, right? It has embeddings that it has learned, and now it gets transformed into how does it do next token generation? Well, the embeddings then get multiplied by the vocab matrix. That vocab matrix then assigns a probability that the next token is going to be one of the tokens in the vocab space that we have, and it gets assigned to a probability to each of the tokens in the vocab space. Right, so vocab space has, let's say, X number of tokens. We multiply the embeddings by the vocab matrix to get to the probability that of each token. And that could happen when we make the prediction for the next token. And so temperature scaling, a way to control the randomness of it. Top K, top P is a way to select, okay, or we're just going to focus on the top K tokens and then renormalize. Or instead of top K, we have top P, focus on all the tokens who have cumulative probability greater than or equal to P. Quantization is all about trying to uh, represent the weights of the learned matrices in a smaller, more efficient format. So from 16 bits to 8 or 4 bits. And we're doing this like millions, like hundreds of thousands of times. And so that makes, in terms of memory, extreme adds up and becomes more efficient. RAG, right, where we are retrieving documents and retrieving the most relevant documents to the search query by doing the dot product, cosine similarity. We have types of fine tuning, which we don't update everything. That would take time. But what Laura does instead is we train AB, which is D by R or R by D matrices, and these are very efficient to learn. But we can control the strength of the updates through the R parameter. Talk about quantization, RAG. And now RAG is only one shot, correct? One shot RAG is you just do the query, it identifies the documents and then returns the relevant documents, and then it builds the answer from there. It doesn't detect anything about if the retrieval is correct, if it should do another fetch. When it does do that, then we move to agents, which we have orchestrators. We have tools which refer to the documents, the API calls. And we have the actual model, which is the brain, which is the LLM. LLM doesn't do any execution. LLM only does the reasoning, and tells what to do. And then the orchestrator then does the execution of those and then returns the response back to the LLM, which then decides, did it answer the question or not? We have this entire loop. There's different models for agentic workflows. Again, tools, as we talked about, search engine database, reasoning step, and then a controller who sends prompts to LLM and then decides what to do next. We'll stop there.